Okay, we're back for some more intermediate motor controls. So far we have talked about starting the motor, and we have talked about reversing the motor, all of that done through our control circuit. Okay, and when we've stopped the motor, basically all we've done is hit a stop button, or we've broken a circuit in the control circuit that powers the motor starter, whether forward, reverse, or both. Okay, but we have not really, when we've stopped the motor, we've allowed the rotor to spin down to 0 RPM on its own free will. We have yet to really brake a motor. In other words, we have yet to bring that rotor to a dead standstill very quickly. And that's what is known as braking, and that's what we're going to talk about today. There's several different ways that we can brake a motor, or bring the rotor shaft down to 0 RPM, which is our ultimate goal in braking. Okay, and we can do these through some mechanical methods, also some electrical methods. But we're going to talk about braking a little bit. We've got a couple of lab experiments for you to work with in the lab. So we're going to jump right into it right now. Okay? And this is braking. And there's several different methods that we're going to talk about that we can use to brake the motor. Okay? There are three ways that we're going to do it, that we're going to talk about. And number one is plugging. The other is mechanical or electromechanical braking. And the third type that we're going to talk about is DC injection. That's an electrical method of braking the motor. Okay. First one we're going to talk about is plugging. Now, what is plugging? Plugging is basically rapidly applying a reversing voltage to a motor that's running in the forward direction. Okay. We're going to rapidly apply a reversing voltage just long enough to bring that rotor to a standstill. Picture it like this. You're driving your car down the road, say 35 miles an hour, okay? You don't have any brakes, all right? So you put it in reverse. You slam it into reverse, and let's just pretend that the drive shaft doesn't fall out in the road, okay? So we're riding along here, you put it in reverse, and you give it the gas, and the tire starts spinning backwards, and then it comes to a dead stop, and before the car actually starts running in reverse, moving in the reverse direction, you stop, you kill everything, okay? That's basically what plugging is, okay? What we're doing is we're running a motor forward, and we're going to apply reversing voltage, slam it in reverse, but only long enough, and this happens very, very quickly, very rapidly, only long enough to get that rotor to start turning back, or to stop turning forward and stop right dead still, at a dead standstill at 0 RPM. In other words, we don't want it to actually start running in reverse, okay? Just enough to stop the forward momentum with the reverse voltage, stop that forward momentum, and then bring it back, okay? Just to where it stops at 0 RPMs, okay? There's a couple of different ways that we can plug a motor, okay? There's the manual plugging, then there's the timed plugging method, and then there's the zero speed switch plugging method, okay? We're going to jump right into these. Manual plugging requires interaction between the operator and the machine. In other words, I'm going to have to hit a push button or some type of a device, some type of switching mechanism to get that forward contactor to disengage and engage the reversing contactor just long enough to stop that rotor, okay? That's kind of tricky because my finger doesn't move as fast as this other person's, theirs doesn't move as fast as mine. You know, there's a lot of variable there. When you're talking about human intervention with a machine, a tremendous amount of variables can come into play. And so it's one simple, inexpensive way to plug a motor or to stop the rotor, but it's very inconsistent, okay? So if you've got a really tight process, you know, that's highly automated in most other parts, you're not going to have somebody stopping a process with the push button method of plugging. But we still want to talk about it, okay? Like I said, it's inconsistent, but it is inexpensive. It doesn't require a whole lot of changes or anything like that. Let's take a look at how at our schematic, and let's see how this actually works, okay? Everybody's familiar with this. This is one nice thing about us moving forward in these classes. We don't have to revisit all the three-phase part. We already understand how it works, the control transformer, so we're going to move directly into this. So we're running along, and we've got our control voltage going through our stop button, and we've started our motor, and this is our plugging switch, okay? This is our plugging switches right here. It's a two-pole push button, one with a set of normally open and normally closed contacts in one switch, okay? So we're running along here, and we're passing through our normally closed contacts, our reverse interlock. We're running forward, everything's happy, okay? We've also got a seal-in circuit from our forward start. So we're running along here, and we've been running, say, 5 minutes, and now we want to bring the rotor of that motor to a dead stop, okay? Here's how we're going to do it. We're going to press this push button. it's going to break the circuit right here. So we're going to de-energize the forward control, and the mechanical linkage here is going to immediately engage this set of contacts so that we have a reversing voltage coming through here, okay, as long as we're holding our finger on the button. But remember, the idea is we don't want this thing to really start turning in the reverse direction. We want to apply the reversing voltage just long enough to stop the momentum of that mass of the rotor. Remember, you know, some of these motors, 50, 75, 100 horsepower, got these massive rotors, so they got a lot of momentum still built up, and even when we de-energize the forward contactor. So what we want to do is we want to stop that forward momentum, and then we want to reverse it just long enough to make it stop, stand still, like we do with the car, okay? So we press the button and we apply reversing voltage. Again, the problem is going to be inconsistency, because I don't know how long that I need to actually actually hold that button in and give it the reversing voltage. And it really depends on what the motor's driving. The load it's under, is it a pump, is it a crane hoist, what are we driving here? So that's, you know, it's a lot of guesswork, okay? And this usually happens so fast you don't have time to watch it go down to 175, 150, 175, 50, 25 RPM and then let off. No, it happens so fast, it's just kind of a guessing game. So there's where your inconsistency comes in. But this is the circuit at which we can manually plug a system, okay, and get the motor to stop. All right, so that's manual plugging. Okay. Also, notice this: there is no sealant circuit for the reverse. We don't want that, because again, the idea is not to keep it running in reverse. Just enough reverse voltage to stop the momentum of that forward rotating rotor. All right, so we don't want a sealant circuit. Okay, so just enough to get it to come to a standstill. All right, that's manual plugging. The other method of plugging stays the same. We're still going to apply the reversing voltage to the motor just long enough to stop the rotor, but this time, instead of using a manual push button with our finger, we're going to allow a timer that you should already be familiar with, okay? That's why we covered it first. We're going to allow a timer to do the work of our finger, okay? Or the human interaction, okay? Again, we're going to use an off delay, okay, because we're going to delay turning that reversing voltage off, even if it's just maybe a quarter of a second, probably not even a half a second. But we want to apply voltage through an off delay, and we're going to use the normally open, timed open contacts, okay? I'll show you the schematic here in just a second. But we're going to use that off delay timer, and we're going to apply that reversing voltage just for the length of time that we got our dial set for our timer, okay? Like the manual plugging system, it's going to require a reversing motor starter, because we've got to apply voltage in the reverse direction. It's fairly consistent for braking, because you have an electronic device doing the controlling that's going to be fairly consistent, okay? Here's where it's going to get a little tricky though. As long as you are controlling, or as long as you're driving the same load on the end of your motor shaft, okay, whether it be a pump or whatever it is, as long as that's consistent, then our timer is going to stay, we're going to get the consistent results out of our timer. In other words, it's going to stop it and bring it to a dead standstill fairly consistently, okay? The problem is you can't always tell if a load's going to be consistent or not, okay? The pressures may change in your pump. Again, when temperatures change and fluids start to, viscosity levels start to change, that impacts how much load or how much work a pump has to do. If you're picking something up with a crane hoist, for example, all right, and you go to brake that motor or something like that, or you're carrying something with an overhead crane, you may not be picking up the exact load every time to the exact pound, okay? So you'll set your timer to stop the rotor at a certain point, but if you need more or less time, then that gets a little inconsistent. So it's good as long as the load is consistent, but if your load varies, then you're going to constantly be changing that timer. It's not a real effective method. But like I said, if your process is consistent, it's a good way to do it, okay? Here's how this schematic is going to work, okay? Now, notice that we've got a timer relay in this schematic, okay? And we have the off delay timer that's going to be normally open, timed open, all right? So let's step through it. Also, we need to pay very close attention to, we've got our reverse and our forward interlocks. That's going to be critical here. So we are running along, we've got our motor sealed in, okay? And we're running in forward, okay? And as long as we are running in forward, we're energizing our timer. Now remember, on an off delay timer, the timing process doesn't start until we de-energize the timer. That's when it starts. Remember, we said that on an off delay that the timing happens on the back end of the timing process, okay? So we are energizing the timer, but our contacts are not doing anything just yet. Okay? Or our contacts have changed, but they haven't actually started the timing process yet. So now I'm going to hit the stop button, okay, right here. We're going to de-energize the forward motor starter coil. That will open up this set of contacts so it'll be normally open, or it'll open back up, excuse me. And we will de-energize the timer, okay? When we de-energize the timer, okay, that's when these contacts start their timing process. Remember, they're already closed as a result of us energizing the timer. Off delay timer changes immediately, okay? The contacts do. Now, they're going to stay in this closed position while we're, until we de-energize, all right? We de-energize this, and it de-energizes the timer. It also opens up this set of contacts right here. I mean, excuse me, closes it back. Let me back up. So, we're running it forward. Our contacts are closed. We are energizing the timer, okay? At the same time, when we're running forward, this set of contacts is open, so we're not applying power to the timer relay contacts. Now, remember, when we started in forward, we energized this timer relay, and it immediately closed these contacts. It's just going to hang out here until we de-energize. So we've opened this set of contacts, so these have closed, but there's no power going to them, all right? So we de-energize the forward contact by hitting the stop button, okay? These open back up, our timer coil dies, all right? But these now close back to the normally closed position. Remember, we said that these switch to the closed state as soon as we energized it. Now, as soon as we de-energize here, it's going to start the timing process. So we've got voltage coming through our normally closed contact, through our timing relay, to our reverse. Now, it'll start running in reverse, and it'll stay running in reverse until these timer contacts time out. These things will be set for something like maybe a quarter, maybe an eighth of a second, just really, really fast. Just enough to apply a reversing voltage to get it to stop, okay? So, I know I've probably got a little confusing here for you a second. I'll just step through it one more time very quickly. We're running forward, okay? We're sealed in. Our contacts are closed here, and we've energized the timer. Also, these contacts have opened as a result of running the motor in forward. Okay, we're running along. These contacts have closed because we've energized the off-delay timer. Okay, they're just kind of closed, hanging out. No voltage going to them because the normally closed contacts are open as a result of us running. We hit the stop button, de-energize, opens up, de-energize, closes these. Okay, and now the timing process starts as a result of this dying off. Okay, so voltage is now allowed to pass to the reversing coil. We're giving it a surge of reversing power, okay? And we're going to do it as long as these contacts are staying engaged, and these will time out, open up, and kill the reversing. Our goal is we want to set the dial on our timer to just where when it goes in reverse, it doesn't actually start spinning the motor backwards, just enough to where it needs to come to a stop, okay? So that is the time plugging, all right? Now, the third method that we're going to talk about as far as plugging is the zero speed switch. This is a zero speed switch right here. A lot of them look very, very similar. I've seen a lot of these. Alan Bradley makes a really good one. But basically what this does is attaches to the end of a motor shaft, okay? Or it's driven by the motor shaft some way or in some form. Sometimes I've seen them driven by a belt. I've seen them hooked up with Lovejoy couplings as well. But the idea is that it is detecting motor shaft speed, okay? So, or whatever the motor is driving, it's detecting that speed, okay? The way this works is there's a set of contacts inside this switch, all right? And it uses centrifugal force, all right? And so as this motor starts to spin, the centrifugal force on the shaft gets greater and greater. Well, there's a set of contacts in here like this that are closed up. And as it spins faster and faster to get its full speed, the centrifugal force will force these contacts open. And as long as that motor is running at full speed, these contacts are going to stay open. Now, when it drops below a certain speed, like when we shut the motor off, when it drops below a certain speed, the spring pressure inside here will force the contacts to close, okay? So the spring pressure will be stronger than the centrifugal force, so they'll start to close back up, okay? That's how the contacts are made, how you make and break the contacts in the centrifugal switch, okay, the zero speed switch, okay? And you'll see this little adjustment screw right here. That you can change the pressure at which is that's applied to the contacts to either require more centrifugal force to make them open up or to require less. You can adjust them in or out. The more you run it in, it's a little Allen screw right here. The more you run it in, the more pressure it's going to take for that centrifugal force to overcome and open the contacts. Likewise, you back it out, it's not going to take as much centrifugal force. All right, so that's how that works. All right, and again, the contacts will engage a reversing motor starter, okay, and just long enough for it to apply that reversing voltage, okay. Here's how this works. And here's a new symbol for you. This is a zero speed switch right here, okay. It's labeled as a plug-in switch, but we can tell by the arrows, these arrows, bidirectional arrows right here, that it's a zero speed switch, all right. So we're running along and forward, everything's fine, okay. And as soon as that motor spools up in the forward direction, these contacts will close, okay? So let's say we got it adjusted to where it closes the contacts at say 300 RPM, okay? Shortly after startup, so we've got 0, 100, 200, 300 RPM, and it closed and it runs on up to 1800 RPM, all right? So we've got our motor running and our contacts are closed, okay? And we're running for, I don't know, 5 minutes or so. We decide we want to stop it. Okay, and also remember these normally closed contacts right here on the starter are open. So we've got voltage coming through our contacts, and they're going to park right there because this normally closed switch is open as a result of the forward contact being pulled in. So we decide we want to stop it. All right, and this is going to be almost, you have to almost think slow motion with me, okay, time lapse, so to speak. We hit the stop button. Okay, forward contactor disengages, all right? We're still running, let's say we're at 1800 RPM, okay? We're still running 1600 to 1500 RPMs, enough to where it keeps that centrifugal switch engaged, okay? So we're spooling down, but we've not dropped below the 300 RPM level, okay? So we're spooling down, and our contacts are still engaged, so it's going to allow power to flow through here. We've de-energized, so these contacts have closed back, and it hits our reverse starter, and we're applying reversing voltage to the motor. Now, as soon as that reversing voltage is applied to the motor, that RPM of the motor shaft is going to come down rapidly. So when it drops down, 15, 14, 13, 9, 8, 7, 300 RPM, that switch will open up, okay? Because the spring pressure will be great enough to overcome, and then it will open these switches back up. And when it does, it kills the voltage to the reverse side, okay? Now again, we can adjust this to where as soon as it shuts off and say spools down from 1800 down to say 1500, we can go ahead and have these switches open up. We can adjust that, the amount of RPMs that the shaft has to apply to the switch in order to get them to open back up. But again, this is a zero speed switch braking, or plugging, I should say, which is a method of braking. So those are three methods. We've got a couple of different other methods I want to talk about. One place that you will see sometimes in a zero speed switch used is in conveyors. Okay, and I just happened to find this graphic of these grain elevators and silos. Okay, grain bins. Like for example, on this B conveyor right here is a screw conveyor that the corn or whatever grain material comes up the elevator, is dumped down here, and you've got an auger shaft that's going to carry it over here to this bin right here. All right. Well, if you've got a ton, if we have a malfunction right here, you don't want to continue to feed grain in there and just plug it up and jam it up. Okay. So what you do is you put a zero speed switch like this one on either the shaft of the auger, or you could put it on the motor shaft. The auger would be better, okay, because if this was belt driven, you broke a belt and you were monitoring motor RPM, you'd never know because the motor would continue to spin without belts on it. So it's always a good idea when you're looking at conveyors like this, mount it on the end of the auger, okay? That actually monitors the auger motion. So if we're running along, and let's say we broke a belt that drove the auger from the motor, our zero speed switch would monitor that, and as soon as that it detected that there was no RPM going on here, okay, these contacts in that zero speed switch could be wired into the contacts to the grain elevator itself. So we would quit feeding grain. We'd shut this, actually we'd shut this motor off right here that's driving the vertical belt here, the bucket elevator. We'd shut it off and stop feeding one that can't take the grain anymore, okay? I think that's fairly clear. So we would wire the contacts on this switch into the actual vertical grain elevator so that when it says, hey, I'm not running anymore, you need to stop the flow of grain, it would kill the motor that's feeding the grain elevator and eventually down to the auger here. So that's just an application that I've worked with personally with zero speed switches. Okay. Now there is downsides to the plugging, and one of them is it creates a lot of heat. Okay, in our windings. All right. Whenever you have to slam something in reverse, you've got that counter EMF going on in your windings. It builds heat up. The energy has to dissipate somewhere, and it does it in the form of heat. And the windings wind up taking the brunt of that heat. So that's one drawback of plugging a motor. Okay. The other one is the wear of mechanical load components. Here's a grid coupling that couples your motor with a pump or whatever it is that's being driven. That's a grid type coupling, and it's really robust, but subjected to instant reversal and things like that. That puts a lot of wear on anything that's mechanical being driven by the motor, and so you get you can have grid coupling damage. We've worked with some of the Lovejoy couplings in 1002 where you hook the generator and alternators up. Those have the little rubber spiders in there, slamming it back and forth like that, really tough on the jaws and also the coupling of the spider in that Lovejoy coupling. So there's always a sacrifice for when you're plugging. Something's going to have to give. Something's going to be your weak link. So it's typically going to be electrically, it's going to be your windings, and also mechanically, it's going to be your grid coupling, okay, or whatever you've got it coupled up to. All right. The other type we're going to talk about is the electromechanical braking system. All right. And basically, this is a coil that overcomes spring pressure. Again, we go back to the fundamentals of our electricity. I think I've told a lot of you, if you get nothing else, just remember that electricity is all about coils of wire creating magnetic fields. The same applies here with this brake. We apply a voltage to this coil, and a magnetic field pulls these shoes apart, and these shoes will go around a drum crane. I'll show you a crane brake drum, excuse me, and they will clamp down and stop the spinning of a drum shaft. Okay. So in the event we lose power, okay, we've got a spring pressure that will clamp down on a brake drum and prevent it from spinning. If you lose power, you just want something to come falling out of the sky, particularly with a crane, or have a runaway motor because you don't have a braking method. Let me put it into context for you. This is an overhead crane, okay, and it's got a huge gearbox and motor and a hoist for the hoisting mechanism, and in order to keep a load suspended, we have to have a method of braking or holding it in place, okay? And this is how it's done. This is the spool, this is the cable for the overhead hoist, okay? And as the motor turns on, it unspools the cable and will lower the hook block there, and it will also retract it, okay? Our motor will be over here on this end, and this is our shaft driving it, okay? And this is a big brake drum on the end of it. This is the gearbox behind us, okay? So we're running along, and when we start the motor, we will energize the brake coil, and that will pull these shoes off of this brake drum and allow the motor to turn it in one direction or the other. If we have to stop the hoist from going up, this could also be for the traverse or for the trolley or anything else, but if we have to stop that, or if we lose power, okay, these springs, there's a spring mechanism in here that will immediately clamp those closed so that the load will stop coming down or stop going up. If you're running a traverse method, I have seen cranes run out the end of a building before, overhead cranes, and I've seen them run out of the building before from malfunctions. with the braking mechanism. So if we lose power, we want to stop that crane immediately and all the functions with it. But basically what it does, it's got electromagnet right here. We energize it when we want to go forward. It energizes the motor and this coil at the same time. They're in parallel, and it will open up those brake shoes and allow it to freewheel, or not freewheel, but be driven by the motor. Okay. And as soon as we shut the motor off, we shut the coil off, or in the event of a power failure, that happens too. We'll clamp those brake shoes down and hold that and suspend that load. Okay. Measurements between these are critical during inspections, but because you don't want to have you don't want to have any slippage at all. Okay. So it's critical that you follow the proper procedures to set these brakes up. But again, this is just sort of how this works. Okay. And the other way we do some electromechanical braking is this is the one you're going to be working with here in the lab. This is basically a coil, okay, and it's got little discs in there, and there's a little clapper mechanism in there, and it will clamp those disc mechanisms, and we apply voltage in order for it to freewheel so the motor can run. Okay, motor shaft will have a load. It goes through the shaft, through the brake here, and when we start the motor, we apply 24 volts to our coil, and then our coil will release the braking mechanism and allow it to run. Now, in the event we have a power failure, we lose our 24 volts in addition to the motor voltage too. So the motor stops trying to turn, and we lose the voltage on the braking coil. When we lose that braking coil voltage, it locks up and shuts the motor down and stops it immediately. Okay, but this is another electromechanical type brake. You'll see it in the lab as well. This is a little bit different type, but it does the same thing. It's got these plates and these discs in there that get clamped down and squeezed, much like a disc brake system on a car, but except for instead of using fluid power, we're using electrical power. Okay. All right. The next method that I'm going to talk about is DC injection. All right. This is kind of a cool, I think, one of the coolest ways to stop a motor. What we're going to do is we're going to take DC voltage, and we're going to connect. We're going to apply DC voltage to one set of windings on a three-phase motor. Okay. So in other words, this should look very familiar to you. Okay. So in other words, we're going to take one set of windings, and I'm picking the windings 1 and 4. Okay. We've got the one on one end. Goes around and around inside there, comes out, the other end of it's 4. And what we're going to do, we're still hooked to the three-phase, but we're also going to hook a couple of wires in here that will apply DC voltage when we tell it to. All right, what we're going to do is, what happens is, with three-phase voltage, we created that rotating magnetic field because you had A pulsing, then B stronger, then C stronger, and you had a constantly rotating magnetic field, and our rotor chased that magnetic field. Well, what we're going to do first is we're going to, first of all, remove the rotating magnetic field. We're going to open up the motor starter, okay, and stop applying three-phase voltage. And then we're immediately going to put DC voltage on one set of windings, okay. And so instead of having a rotating magnetic field, now we have a stationary magnetic field, okay? So, I'll back up just a little bit here, all right? One of the things we've got to do, though, is we have to have a DC voltage source, all right? And we get this through a rectifier, a full bridge rectifier, all right? And I'm going to step you through this because I don't think you've had this just yet. But we're going to take AC voltage, and through a series of diodes, we're going to come out with DC voltage. All right. Now, we install these rectifiers, and basically what happens is the positive side of our AC sine wave, okay, positive side will be allowed to pass through the diodes. Notice these diodes are configured differently. They're the same diodes, same type of diodes, it's just some are soldered in this way and some are soldered in the other way. What these are biased diodes. In other words, this is a positive bias diode. It will allow positive voltage to pass through, okay? But it's going back to the back side of this triangle here, for lack of better words. Okay, it's going through here, okay? But if it tries to enter here through in the opposite direction, it blocks it, okay? So the positive sine wave is forced to come in one direction. If it tries to go through, this diode is soldered in so that it blocks it. So only the positive can go. Now, when we reverse and go into the negative part of our sine wave, okay, then the negative side is going to come through, and it's going to go through the negative bias configuration, and it's going to allow it to pass through the negative. If it tries to go through the positive, like on this direction of this diode, like this one did over here, it's going to get blocked. So it's going to be forced to come out here. So basically, you're taking the positive and negative, and you're coming out with a DC output. Okay, that's as close as you can get to pure DC without a battery. A battery is pure DC. But with a rectifier, you're going to kind of get a fairly smooth ripple of positive and a fairly smooth ripple of negative to where it looks like just straight DC. But we are rectifying the AC sine wave and making DC voltage. That's where we're going to get the DC voltage to apply to terminals 1 and 4, or winding T1, T4 in our three-phase motor. Okay. Here's a little graphic I got for you. I made this one up here. You got this. We're going to use these set of windings right here. Okay. So when we're running along, we're chasing that magnetic field. In this case, we're kind of running this direction according to the arrow. So we've got A phase peaking, B phase, C phase, and our magnetic field is rotating. All right. We take the three-phase away, okay, and then we immediately put DC voltage on one of the windings. Okay. So we have, instead of a rotating field, we've got a solid magnetic field, and again, the rotor is attracted to that solid magnetic field. Okay. It's not going to chase it around in a circle because it's not running in a circle. It's going straight across this set of coils, this one set of coils. So we've got a strong magnetic field right here of DC voltage, and it will lock in just like that, okay? And it will align itself with the magnetic field. There is no magnetic field in the other coils at this moment because we took the three-phase away, and we're not hooked to the other phases. We are just hooked to this one set of coils right here. So the rotor is going to, it'll be spinning, and we'll slow that mass down enough to where it will just lock in right here. It's going to just like that. All right. So it'll stop it dead in its tracks because there's a magnetic field going on that rotor is rather attracted to. All right. And it's going to stay stationary for us. All right. We start the motor back up. We take this DC voltage away. Start the motor back up. The rotating magnetic field comes in play. The rotor starts chasing after that rotating magnetic field. Take it away, and then we immediately apply DC voltage, which is just a stationary magnetic field. That rotor is going to stop and be attracted to it. Okay, so that's how we do DC injection. All right. Here's sort of how the schematic works. This is the three-phase part of it. Okay, so we got L1, 2, and 3. We're running along through to our motor. Okay, and then at some point we open up this set of motor contacts on our starter. Okay, and we bring in another set of contacts that allows the voltage to come in here to feed our rectifier. And going into it is two phases of our AC, okay? And we're going to come out DC. So this is going in AC, this is coming out DC. Should be familiar with you for that, the wiring exercise you did with the proximity switch. Remember you had the L1 and neutral going to your power supply, and it came out positive, negative DC. Sort of the same thing here. We're feeding the AC, it's coming out DC. These contacts, these two contacts, you only need two because the positive and negative, this is not three-phase. We are feeding the positive and the negative across these contacts into the windings of the three-phase motor, and then the motor is going to stop because it's lined up with a stationary magnetic field as opposed to a rotating one. All right. Here is the control circuit diagram of that. Okay. We're running along here. Our timer relay. All right. Start, stop. We're sealed in. Okay. And then we decide we want to stop. Okay. And this is a off delay timer. And we're energized, so these contacts are closed already. They're closed right now, okay? And we're running, and I hit the stop button. Our forward contact opens up, or de-energizes, excuse me. All right, remember, this is closed, and now we're going to start the timing process. This contact's closed back because we stopped running and forward, and it will run and keep these contacts closed right here, this B set of contacts. Just long enough to get the rotor to stop, okay, and then as B is closed, that's when these two sets of contacts right here are closed, and we apply that DC voltage to our three-phase motor. That's kind of a lot to take in, but fortunately you're going to have an exercise in the lab where we're going to hook up three-phase voltage and then stop it with DC. This is the panel that you'll use, and just give a little heads up on this one. Here we've got AC input, okay? We're going to apply our power to our transformer. It's going to step it down to 24 volts from 120, step it down to 24, and here's our rectifier. This is the actual rectifier itself. The black and the red wire are our hot wires going from our AC, and the two green wires are the negative, or the positive and negative DC coming out. So we're going to step it down from 120 to 24, and then we're going to rectify it. So we're going to have 24 volts DC coming out of this. We're going to take it from here, apply it to T1, T4 of our three-phase motor, and we're going to lock it in there long enough, just long enough for it to stop the motor. Okay, stop the rotation of that rotor. All right, that's how this works. You got some reading in your textbook that will also help explain this as well. But other than that, that's what our braking is. That's the methods of braking that we're using. Come in the lab, you're going to be working with DC injection. You're also going to be working with electromechanical. And then we'll see how DC injection plays its part when we start getting into drives, because drives will break a motor as well. And one of the ways is using a DC injection parameter. So anyway, that's braking. If you've got questions, come see me in the lab. We'll talk about it. You'll have some lab exercises. So far, everybody's doing really well. I know that some of you have struggled a little bit with some of the labs, but that's okay. It's challenging, and that's the best way to learn is when you're challenged. If it was a breeze, you probably wouldn't learn nearly as much. But hang in there. We're getting close to the end. But again, this is braking, and if you've got any questions, come see me. Hope you got something out of this, and we'll see you in the lab. Thanks a lot.